NDAs are recording. Everybody who wears green gets 5 books.
Serious?
Yeah. Okay.
That's right. Yes, underwear counts. Okay. So today we're going to talk about semi-supervised learning and never-ending learning, 2 of my favorite topics. And we've talked a little bit before about semi-supervised learning because that's really this question. Semi-supervised learning has to do with the question, how and when can unlabeled data help us approximate some function f? And when we say unlabeled data, we mean just that we only have the x's without the y's that go along with them. So now that we've talked about the PAC learning setting, we could talk about the semi-supervised learning setting as follows. And this is basically the way we're going to think about it today. We have some set of instances drawn from some underlying P of X distribution that we don't particularly know, but it's fixed over time. We wish to learn some function from x to y or conditional distribution of y given x. Our learner has some set H of possible hypotheses. And in the past, we said, well, and then we'll provide labeled examples, shown as L here, where each labeled example is some pair x sub I and the y sub I that goes along with it. And here we're going to say, well, we also have some unlabeled examples, which are just more x's without the accompanying y's. And our goal, as typical, is that we want to find the function that minimizes. Our estimate is going to be the hypothesis H. We want the one that minimizes the probability that it'll disagree with the true function f. Okay? So it's just the same setting we've been talking about before. And we did discuss this once already in the semester before the midterm. Remember? Good. Good. So EM, that's right. EM is exactly one answer to the question of when can this kind of unlabeled data help. And when we talked about EM, we even used this little example here where we said, well, we know the labels for some of those x's, but not for all of them. And what can we do? And what we decided was, well, with EM, at least we could estimate the parameters that maximize the expected full data likelihood. Now, it's a good idea. There are roughly 2.5 other ideas that I've seen in the field. One of them that we're not going to talk about today, but which, if you're interested in this, I encourage you to read this very nice paper by Dale Shermans called Metric Regularization. It's an idea for how to use unlabeled data to detect overfitting. And roughly, and if I had to describe it in a sentence, I would do it this way. I haven't figured out how to do this. I would do it this way. I'd say, think of growing a decision tree and trying to detect when it's getting so big that it's overfitting the data. And the way you can use unlabeled data to do this is when you grow the tree larger, you could look at how the labels assigned to the unlabeled data by the new tree and the old tree compare. And if those are changing faster than their assignment of labels to the training data, that's kind of a signal that maybe it's changing too fast and you're overfitting things. Or if it changes slower than that. If the training data if fitting the training data is happening faster than the difference in the labels on the unlabeled data, that might be a signal that you're fitting the training data too much, and therefore you should be wary that maybe you're overfitting. And this paper actually does a very nice job of formalizing that intuition and showing some experiments showing that indeed you can use this idea to detect overfitting in some cases. So it's a nice idea. The one that we are going to work on today is an idea called, people use different terms. Some call it co-training, some call it multi-view learning, some call it co-regularization. But it's a simple and wonderful idea, which is this. The idea is sometimes we have problems where we can make an additional assumption that lets the unlabeled data be useful. And in particular, sometimes we have the features that are describing X contain redundant information about the Y that we're trying to predict. And if we think we know something about that redundancy, we can train two classifiers using different subsets of the features. And then on the labeled data, we'll train those classifiers to predict the Ys that we know. But on the unlabeled data, we also want them to at least agree. So that's the intuition of co-training. And let's see an example of that. Here's one of some of you may know Professor Christos Faloutsos. It's one of my favorite pictures of Christos from before he came to CMU. But let's use this as an example to think about suppose you want to train a classifier for web pages. And you want to classify pages into faculty home pages or not. And so I would say here's a positive example of a faculty homepage. And the features that I'm using to describe this example includes both the words that are on the page itself, but also these hyperlinks that point to the page from elsewhere. Okay, so somebody else authored a page that says, oh, here's Professor Faloutsos, and they point to this. And somebody else authored a page that says, my advisor, and it points to this page. So I would say this is a prototypical example of the kind of redundant features that we would like to see in order to use this co-training idea to leverage unlabeled data. It's redundant in the following sense. If I give you this example, it's obvious to you that it's a positive example of a faculty page. So these features are sufficient. But in fact, if I only give you that half of the features, you could probably still tell me whether this page here is a faculty page or not. Why else would it say Professor X? Okay, so these features are sufficient to classify the page, and so are the other half. If I show you these features instead, you could still tell me yes or no, is that a faculty homepage? So in this sense, those two sets of features taken together are redundantly sufficient to make the classification that we're interested in. And so if we have data of that form, we can get a lot of leverage out of it. So in particular, what we could do is, if we want to train and we have some labeled data, suppose I give you a dozen labeled web pages, labeled as faculty home pages or not, and then suppose I give you 1,000 unlabeled web pages. So one thing you could do is you could say, well, I'm going to train not one classifier, but two. I'll train one classifier that uses just the hyperlinks, and I'll train a second classifier that uses just the words on the page, those two sets of features we looked at. And what I'll do is, first I'll use the labeled data, L, to train those two classifiers. They may not be very good because I don't have that much labeled data. But hopefully they'll be better than random. And they'll probably be, depending on the classifier, pretty good if they see an example that's almost exactly like one of the training examples. They'll be very unconfident if we show them something very different, maybe. But then what we could do is we could use the unlabeled data according to the following algorithm. That is, once we train these kind of weak G1 and G2 functions, both of which are trying to predict yes or no, is this a faculty page? but one of them is using the red hyperlink features, the other is using the blue words on the page features. Then we could let both of those go to the unlabeled examples, U, and just pick the ones in which they're most confident to assign a label. So maybe the hyperlink classifier will find another page, or sorry, another hyperlink. It only gets to look at hyperlinks. Maybe it'll find another hyperlink that says my advisor. That would be great, because then it can confidently predict that this hyperlink page pair is indeed a faculty homepage. And then maybe the page classifier will find something that it can be highly confident in too. But since those hyperlinks were authored by a different person than the words on the faculty page, there's some kind of independence. They're somewhat independent features. And so the things that are easy for the red hyperlink classifier to classify are not necessarily going to be the ones that are easy for the blue page classifier, and vice versa. So they both get to kind of cherry pick what's easy for them. But every time they label something, they bring in both the hyperlink and the web page pair, because that's the example. So in this sense, these two classifiers are co-training each other by starting with a set of labeled data, and then on each iteration, retraining and looking at more of the unlabeled data, cherry-picking the examples that are easy for it, and then adding these as self-labeled examples, which are going to be used by both classifiers to retrain. So you see, it has very similar to EM kind of feel to it. It's an iterative algorithm. But we're making this, well, we haven't really made any additional formal assumption, but we're about to. It turns out this algorithm works particularly well, provably well. Maybe I shouldn't say exactly this algorithm. There exist algorithms that work provably well if we formalize this assumption about the features being redundantly sufficient. But even in practice, this one works okay. So for example, here is this algorithm applied to the problem of classifying web pages. In this case, it's labeling pages as academic course home pages or not. It's given 12 labeled examples and 1,000 unlabeled web pages with their hyperlinks. And on the first iteration, the two classifiers have, given the labeled data and training only on the labeled data, have the error rate shown here. And then with different iterations, on each iteration, the two classifiers then go pick up more unlabeled examples, self-label them, put them in the pool of labeled data, retrain, and iterate. So by the time this iterates 40 times, you see that the error rates for both classifiers have in fact decreased, even though it's kind of a rocky ride. So there's a lot of variance in this over time. Mm-hmm.
So what are the unlabeled data that you actually translate? The one that both classifiers agree on the label?
No. So the unlabeled data that gets added is not the examples on which the classifiers agree. We allow classifier 1, G1, to label the P and N, P positive and N negative examples from U. And it picks the ones in which it's most confident, ignoring the other view of the data.
I mean, so the both classifiers share the same set L, right?
They share the same set L, but L, every example in L is this concatenated set of features. Some of the features are the words on the page. Other features are words on the hyperlinks. And they get these two views. The red classifier only gets to look at the hyperlink words. The blue one only gets to look at the page words.
I mean, for example, there are some of the examples that both label as positive, and some of them one positive, one negative, and some of them one positive, the other not sure. And so, which of these do add to L?
Right. So the algorithm has, each one can just add labeled examples. If they happen, It's not that common, but if they happen to pick the same example to label and they label it differently, then we just have noisy data. But the algorithm does precisely what this says. Each of the two independently picks new examples from the unlabeled pool, adds it to the set of labels, and now we train on everything. And if there's the hyperlink classifier adding it, it adds, of course, both the hyperlink and the web page features.
I mean, what if the G1 labels it positive and G2 labels it negative? So which? Right,
you're asking the same question you just asked. If one of them labels it positive and the other labels it negative, they both go in. And now we have noisy data. The same example appears once with a positive label. It appears again with a negative label. Uh-huh.
So this idea still applies to one classifier, right? What's the benefit of having two classifiers here?
So let's see. Yeah, so you're asking the right question. It's just, well, it's kind of cute, but why would we do this? What's really the benefit? So intuitively, the benefit is we want to squeeze information out of unlabeled data. And if we really believe that these two views are redundantly sufficient for doing the labeling, then we should somehow design an algorithm that leverages that assumption. And the reason is, in a sentence, the reason it's going to turn out to be useful is for every unlabeled example, the system doesn't know whether it's positive or negative, but it does know that the two classifiers must agree. It's okay if they both label it positive. It's okay if they both label it negative. If one says positive and one says negative, then it's probably wrong. Mm-hmm.
Is this guaranteed to converge?
This is not guaranteed to converge. So let's look at... So this is not my favorite co-training algorithm. There's a better one we'll look at in a sec. But it gets the idea across very simply. And so now if you think about the setting that we're talking about, we could characterize it this way. We're trying to learn some function f from x to y. But our features that we have for every one of those instances, x, can be factored into two sets. We could have, say, the hyperlink features and the web page features, the web page words, for example. And if to formalize this setting, the assumption that I want to make is that there are some functions, G1 and G2, that only look at one. G1 only gets to look at x1. G2 only gets to look at x2. So the assumption that I'm making is that there exist functions that can be defined over the hyperlink view, G1, and over the words on the page view, G2, such that those are actually equal to the f that we're trying to learn. It's just a way of saying that x1 and x2 both contain enough information to assign the label. Okay? So let's call this the co-training setting. This is the assumption that we're essentially going to make. Now, if that's the case, then intuitively you can see for any unlabeled example, it'll be helpful to train G1 and G2 so that they agree on all the unlabeled examples. But here's a precise thing we can say about this setting, which is kind of interesting. So if we're in this setting, where we assume there are these G1s and G2s that can look at the different views of the examples and classify things, then if we assume that x1 and x2 are conditionally independent given the label, and we assume that the function we're trying to learn is at least pack learnable from noisy label data, that is, it can learn to some epsilon and delta that we choose. Roughly, that's just saying that you can learn the function if you have enough label data. Then, it turns out that function is pack learnable from a polynomial number of unlabeled examples, provided that we have a weak initial classifier that's at least better than chance. And where do we get that weak initial classifier? From the labeled examples that we have. Okay, so this is kind of interesting. What it says is, basically, we can learn to arbitrary epsilon delta. Remember epsilon delta in our pack learning setting. To any probability that we choose and any error tolerance epsilon from unlabeled data, provided we have enough labeled data to start off with a better than chance classifier. And this is not a theorem about this particular algorithm. It just says there exists an algorithm for doing it. Mm-hmm.
So if I have a whole bunch of features that I know nothing about, would it be possible to use this algorithm some way to check which of those are redundant?
Yeah. It's so people have. It's a great question. If you're in the back, the question was, is there a way to automatically detect that some subset of features are redundant? I would say the jury is still out on that, and there have been several attempts to do that. There have also been some experiments. Steve Minton, for example, did an interesting paper where he picked random subsets of features and showed in some cases, although I could never figure out quite why, that in some cases it helps even if you just choose random subsets of features. So I'd say there's an interesting, there are some papers on that, but that I consider it still an open question, how to do that well. That could be a good topic for a project. Okay, so here's another interesting thing to think about. If we're in this setting, and again, the setting is that both x1 and x2 can be used independently to predict y if we can learn the right functions. Here's another thing. It turns out in this case, we can use the unlabeled data to estimate the true error of the functions g1 and g2 that we're learning. Seems kind of interesting. And here's the idea. Suppose, actually, let me draw it this way. So I think of the problem setting roughly is we have one function, we'll call it g1, which is trying to predict y from x1, right? And we have another function, we'll call it g2, which is trying to predict y from x2. Okay, and so we train these with whatever algorithm we like. So we have a g1 hat and a g2 hat. Some estimates of what those functions are. And now we want to know what's the true error of these functions. And it turns out that we can get a bound on that by looking at how often they disagree on the unlabeled data. And the reason is quite simple, actually. If you think about what's the probability that they're going to disagree on a randomly drawn x? Okay, so again, we use the same notion of true error that we used when we talked about pack learning. We say the error, the true error, is just the probability taken over p of x that, I'll call it g sub I, of x will disagree with the truth. Okay? Just the probability that a randomly drawn example will be misclassified. That's what we mean by the error rate. So if we ask what's the probability that they disagree, what we mean is the probability over that same p of x that g1 of x1 will disagree with g2 of x2. Right? So we give them some example. What's the probability that they'll disagree? Okay, so if we think about it, there are only two ways they could disagree. G1 might be correct and G2 might be incorrect, or vice versa. Otherwise, they're going to agree. Okay, so let me say E1 is the true error of G1 and E2 is the true error of G2. Then what is this probability in terms of E1 and E2? Well, if we assume that they make independent errors, which may or may not be a reasonable assumption, but if you go back, that was also one of the preconditions in the theorem we looked at that said we could pack learn from unlabeled data. And if you think about even the example of the web page and the hyperlinks, if those are written by different people, then it's not that unreasonable assumption to think that, conditioned on whether in fact this is or isn't a faculty page, that's the value of y, that conditioned on that, the words on the hyperlinks will be conditionally independent of the words on the web page. It's not a ridiculous assumption. And if that's the case, then these are going to be independent errors because they're looking at independently drawn evidence. So let's just, for the sake of argument, make the assumption that these G1 and G2 are making independent errors. Agree. Well, the probability that G1 is right, that's just 1 minus E1. Right? And that G2 is wrong, well, that's going to happen with that error rate. Plus, well, just 1 minus E2 times E1. Right? So this is the probability of them disagreeing. And I've written it in terms of the true error rates, E1 and E2. So think about it this way. If I give you two classifiers, and I don't tell you what their error rate is, but you have 1 million unlabeled examples, and you see they disagree 1% of the time. Okay? And now I give you another pair of classifiers, and on the same data, they disagree 50% of the time. Which one do you think is more accurate? It's a no-brainer, right? You're going to pick the ones that hardly ever disagree because if they're making independent errors and they're not disagreeing, they kind of have to be right, or they have to be wrong 99% of the time. That'll work too. But I tell you that they're better than chance accuracy, and now you see this phenomena, then you're going to say, okay, I'm going with the ones that hardly ever disagree, because if they're better than chance and they're disagreeing 1% of the time, how could their true accuracy be greater than 1%? So actually, let's take an example. Suppose that E1 it's 90% accurate. It makes errors 10% of the time. And E2 makes errors 10% of the time. Then what is the probability that they'll disagree? Well, that's just going to be 1 minus E1, so that's 0.9 times E2. Plus 1 minus E2. Okay. Okay, and that's going to be 0.09 plus 0.09. Okay, so this one had gone in the other direction because it's easy to do the arithmetic here. But so if I have two things that actually have true error 0.1, then the expected disagreement, the expected rate of disagreement over unlabeled data is 18%. And so if I see a disagreement of 18% on unlabeled data between these two things, and I assume that they're making independent errors, and also that they have the same error, then I can assume the expected error rate of those is 0.09. In other words, they're 91% accurate because they disagree, because they agree 82% of the time. So if I assume that they're not equal errors, then you can see that it's not a invertible function exactly. But But nevertheless, it turns out this holds up. So in a pretty solid way, in fact, here's a much more intricate way of saying the same intuition. This is due to a paper you can find by Dasgupta. Basically, what he's saying is he's using H1 as hypothesis 1, and instead of G1 and G2, he's using H1 and H2 for his notation. But then he's saying the probability that H1 will not predict the value I, given that the true function f predicts the value I, given that H1 doesn't abstain. In this, his theorem, there's this additional intricacy that H1 is allowed to abstain if it's unconfident. But the probability that it'll disagree with the true label is bounded by the probability that it'll disagree with the other view, H2. And there are some details in here which I don't want to take the time to go into in this lecture, but if you're interested, it is an interesting paper. Okay, but the idea is simple. The idea is this, that we have these two functions, one from x1 to y, one from x2 to y, and the reason that making this assumption that we can label y from either view, the reason that helps us leverage unlabeled data is simply because it brings in a constraint that we know these two functions must agree on the unlabeled data. Which brings me to my favorite version of the algorithm. It's called co-regularization. And in the true spirit of this course, it says, well, if we've got some assumption that we want to make, let's go back to basics and figure out what's the objective that we want to optimize when we choose the parameters of our functions. And so now the idea is, whereas before in the supervised learning case, we said, well, let's maximize the data likelihood or the log data likelihood or the get a map estimate if we have a prior. Now we're going to say, yeah, let's maximize the data likelihood, but we're also going to have to put in some term that penalizes the system to the degree that we have a lot of disagreement on the unlabeled data, because we want to also optimize that. And so, for example, if we think about a regression problem where G1 and G2 are predicting a real valued y, for example, from x1 and from x2, then one way, and let's say G1 uses theta 1 as its parameters, and G2 uses theta 2. These might be, linear regression functions or polynomial regression functions. They just, theta 1 and theta 2 are just the parameters for G1 and G2 respectively. That's what we're trying to learn. Could be a Bayes net. Then the idea of co-regularization is that we use an objective function like this. And this is just our usual maximized likelihood over the labeled data. Because what this term says is we take all the labeled data L, and for every x that we find in the labeled data, we want to make sure that y, the true y, minus whatever g predicts, the sum of squared errors over the labeled data we want to minimize. When we talked about regression, we showed that minimizing the sum of squared errors was equal to maximizing the data likelihood under some reasonable noise model. So we'll keep that, just as we would if we were doing supervised training for our regression function. Similarly, we'll have another term that looks just like that, except it'll apply to G2 instead of G1. We want G2 to also make correct predictions over the labeled data. But now, we introduce another term which talks about the unlabeled examples. And here, a common thing that people have tried is just minimize, I guess this should be a subscript, minimize the disagreement between G1 and G2. Okay. So this makes very explicit in the objective function this assumption that we think these two functions should be agreeing, and if not, then there's something wrong. And so this idea of co-regularization, I'm sure you could now sit down and derive a learning algorithm to optimize this. You could just modify your favorite gradient descent algorithm by deriving a new gradient that has this additional term in it, and you'd be off to the races. And this has been shown to be a pretty effective way of doing multi-view learning that's pretty robust to even noisy data, which that first algorithm I presented is not so robust to noisy data. But this one you see we're minimizing over the entire set of examples, this objective, so it's going to be much more robust. Okay, so that's what I want to say about co-training multi-view learning. It's a simple idea, but actually quite useful in certain problems. And if you know about this idea, sometimes when you're formulating your own machine learning problem, you can arrange to have some redundant features in there so that suddenly you can convert that previously useless unlabeled data into data that's going to help you. So it's also kind of advice on how to engineer the framing of your own machine learning problem. So that's the main result. Yes?
So is this, in principle, is there a reason you can only have two?
Good. So the question is there a reason why we can only have two? The answer is no. You can have as many as you like. And in fact, there are some theoretical results where you can show that the more you have, if they're all independent, your learning rate improves exponentially in the number of these different views that you're combining. That kind of makes sense. It's not surprising intuitively that that's the case. But in general, the more views you have, the better. Yes?
How much would do better than EM algorithm? I mean, for example, in the knife-based example.
Yeah, that would be an interesting project. So the question is, how does this compare with just doing EM, where in EM we don't have this explicit objective function term that requires agreement. And so EM allows a little bit more, well, it doesn't require agreement between these different subsets of features. So it allows solutions to the parameter optimization that are not subject to that constraint, so they'll wander from that constraint. The answer is, I haven't seen a systematic study of that question. There is an interesting algorithm called co-EM, which is like a much more EM-like algorithm that tries to incorporate this assumption. But I haven't seen a systematic study of how this compares with EM. My guess, I'd bet a hamburger lunch that if you make up a synthetic data set that obeys this assumption, then co-regularization will outperform EM. And that if you make up one that violates it, then vice versa. But violates the assumption that both views contain the information you need to predict Y. People have looked at what if the views are sufficient to predict Y, but the views are not conditionally independent. Then it turns out the benefit, the leverage you get from the unlabeled data decreases. It doesn't buy you as much. But it still helps as long as X1 and X2 are not deterministically related, as long as there's some non-deterministic relation between them. Okay, so let me end this because I want to move on to a different but highly related topic. And basically what I want to do is give you guys a talk that I gave last week at the University of Colorado on some research that we're doing. I thought it would be fun to try these ideas out on you. But also, one of the key ideas in this, enable the macros, enable the content. Okay. But one of the key ideas in here is very much taking this idea of multi-view learning or co-training and cranking it up to having thousands of functions instead of 2 to try to get even more leverage from unlabeled data. So this is some work that's done by a whole bunch of people. You can thank them for all the good ideas. And it's motivated by this idea. When I talk to my mother and I tell her I do machine learning, she thinks about learning the way your mother would think about learning. And so when I say I'm doing machine learning, she just assumes what I mean is that I'm building computer programs that learn for days and weeks and years, and after a decade or 2, they're going to be really smart. I'm embarrassed to say those are not the kind of algorithms we find in the field very often. But it's an interesting question, why don't we build some of those? So this talk is really about what would it take to build a never-ending machine learning system that has more of the characteristics that you and I have that our moms think of when we tell them we're learning. They know that, first you learn to count. Then you could learn arithmetic after you did it. You could add and subtract after you could count. After that, you could do algebra and calculus. But you had to do it in stages. You had to learn this stuff so that you could then build on it to learn that stuff. And you weren't just learning to count during those first 8 years and arithmetic. You were also learning to walk and ride a bike. And then at some point you learned physics and you learned calculus at the same time. And there was some weird synergy between learning physics and learning calculus that you couldn't have gotten if you hadn't been kind of learning many things and getting some synergy among them. So the research question is here, how can we build machines that do something like that? We don't have the answer, but we have an aspiration and a first system to talk about. So the task then is to try to build computers that learn over years, many different functions, and where learning one thing improves the ability to learn something else. So maybe you can already see the hint toward why I say this is related to multi-view learning. So what we have, in fact, is a system that has been running now for St. Patrick's Day. 14 months. Its 14-month birthday was last week. Started in January 2010. Has been running pretty much 24 hours a day, 7 days a week since then. And it's trying to learn to read the web. That's the task we've given it. It's a challenging task. It won't be over soon. And the inputs to the system are an ontology that defines the categories of things we'd like it to read about and the relations between things that we'd like it to read about. So, for example, we tell it we want it to learn about people and organizations and beverages and sports and emotions. And then we want it to learn relations between those, like which person plays which sport, or which team plays in which city, which person founded which company. So give it a bunch of categories and a bunch of relations. And for training data, for each of those, we give it 10 to 20 labeled examples. If we're interested in universities, we give it 10 to 20 universities, Carnegie Mellon, Harvard, whatever. So that's the input labeled data and the specification of the things that it's supposed to read about. Then we give it the web and an opportunity to interact with humans, what turns out to be about 10 or 15 minutes a day. Although if you want to interact with it, that'd be great. So then it runs, and every day it has to do two things. Its job is to extract more facts from the web to populate this ontology we gave it, find more instances of the categories and relations. And number two, which is just important, more important for us here in this course, we want it to learn to read better today than it could yesterday. And how do we know that if it did? Well, we'd know because we'd look at what it extracted today from the same text that it looked at yesterday. And if it had learned, then it should extract more facts more accurately today from the same text compared to yesterday. Okay, so there's the task. And the current system, let me do it this way. So the current system has been going for 14 months. It has a knowledge base, we call it, a collection of facts that it has read. That's a couple million facts, or beliefs. I'll call them beliefs because they're not perfect. A belief is, for example, Museum Island is a tourist attraction in the city Rome. That's one of the millions of things that it believes to some degree. This one it believes with a ridiculously high probability. But of those couple million, there are 500,000 that it's fairly confident in, and that we consider the kind of promoted set of beliefs that it has. Then underneath that, there's this, kind of like the iceberg sticking up out of the water, and underneath there's a lot of other stuff that it's just considering as hypotheses. And just to give you, this is all on the web, by the way, so we can go there and we can look at it today, as long as Windows Internet Explorer is agreeable. So, for example, here is a set of beliefs that it has recently extracted. So on March 15th, it decided Pujols is an athlete coached by Carlos Peña. Anybody know? Okay, I don't know. Shortridge's mouse is a mammal. Soldier Bugs is an invertebrate. John Scott is a musician. The Sports League NBAs use a Staples Center. Jeremy Brett starred in the movie Sherlock Holmes. So these are things, so that gives you a sample of the kind of variety of things that it has. And I encourage you, but I'm not going to do it now because I just don't want to spend our time this way, but it is rather entertaining. You can essentially browse the knowledge base by asking about any of these things. So, for example, here's Pujols. Believes Pujols is an athlete for several reasons. One is that it found a phrase on the web called rookie named Pujols. And Pujols' personal trainer. And Pujols won the National League rookie. And Pujols hits a sacrifice fly. So it found those phrases on the web around the noun phrase Pujols, and for that reason it has classified. So really, internally, it's just a bunch of classifiers of noun phrases into categories. Pujols' three-run home run, or Pujols' three-run home run. These are fragments of text that it uses to decide that the noun phrase Pujols probably refers to an athlete. Now, how does it know that? We didn't tell it that. This is what it's been learning for the last year, is these different phrases and their relative weights for deciding these things. What else? I see. Okay, so here's some relations. It believes Pujols is an agent in the organization MLB, Major League Baseball. He collaborates with the agent St. Louis Cardinals because it found the phrase Pujols or St. Louis Cardinals first baseman Pujols. It believes he plays for the team St. Louis Cardinals. He plays the sport baseball. Actually, if we can scroll down, I'm not sure I can. Oh, I see. This is nice. So here's something that's particularly interesting. Here's something that's particularly interesting. One reason that it believes Pujols plays the sport baseball is that it founded the phrase baseball-related quotations spoken by Pujols. Okay, so again, the kind of text fragment that it found. But an independent reason, a different view on why Pujols might be a baseball player, is because it has learned a rule, which I can't write on this screen, but it has learned a rule that says athlete X plays the sport baseball if athlete X plays in the league MLB. So it learned that rule because part of its learning mechanism involves data mining this collection of 500,000 trusted beliefs that it has previously read. So after a year of trying to extract this kind of stuff from the web, it now has the ability to look over that collection of beliefs and to try to find empirical regularities in them. And one of the empirical regularities that is found, and it's cashed out in the form of this rule, is that an athlete X plays sport baseball if they play in the league MLB. So that gives you a glimpse of a couple of the ways in which the system is learning multiple functions, and it's using them to kind of co-train each other on a larger scale. Yes?
So earlier you said that they really have to be overlapping features for the system to get the best leverage out of it. And so how do you know in an open question like this which features, since you don't know necessarily features are going to be exposed to? Right. So you're asking, how do we really set up the co-training problem here? So let's move on to that, because that's really what I wanted to get to. So let me just do it this way. So there are really, if you ask me, I think there are 3 good ideas in this system. That took us 4 years to figure out 3 good ideas. Kind of embarrassing. But one of the good ideas is that if you want to take advantage, is the one we talked about. If you want to take advantage of unlabeled data, then, and do a semi-supervised learning problem, and that's what Nell is doing, is trying to learn from that little bit of labeled data and then the web as unlabeled data. One idea is you should couple the training of many functions. So it's the multi-view learning co-training idea, except kind of on steroids. So instead of training 2 functions that have 2 different views of the same thing, Nell has now close to 2,000 functions that are coupled in this kind of network of interconstrained labels and views and so forth. So what I would like to do is show you what I mean by that. So one thing Nell does, and we just saw evidence of it when we were browsing the knowledge base, is it learns this function that, given a noun phrase, has to classify it, for example, as a person or not. In fact, you can think that's exactly what Nell is doing. It's learning a whole bunch of functions that are classifiers of noun phrases, and also of noun phrase pairs, like Pujols and baseball is a pair. Does that satisfy the birthday of person relation? No. Does it satisfy the person play sport relation? Yes. Okay, so it's classification problems all over the place. So for classifying whether a noun phrase is a person, one view that the system can use is to look at the text fragments that occur around the noun phrase. If we see X is a friend, X just might be a person. So that's one view. A very different view is to ignore the words around the noun phrase and just look at the morphology, just the internal structure of the noun phrase. If I say to you, I've got a noun phrase, Halka Jelinski.
Okay, I'm not telling you anything about the context around that. Do you think that's a person or not? Yeah, so do I, because it ends with the 3 letters SKI. It's probably a Polish person. So there are regularities in the way that noun phrases are made up out of characters. And a different view is to just look at that. Does the word end with ski? Is it capitalized? It's more likely to be a person if it's capitalized. We don't know what all the features are. Nell doesn't know what all the features are, but it's got it's got a grammar for generating thousands of these kind of features. And that gives it a different view of the noun phrase, independent of this one. Actually, conditionally independent of this one, all approximately, given the label. So there's the co-training step. Actually, it doesn't stop there. There's a third view, which is HTML structure surrounding this noun phrase on particular URLs. So this view of the data involves features like this. Here's one feature in this view. This feature says if you go to www.celebrities.com and you find a li HTML command followed by the noun phrase, followed by an end li, then it's probably, well, that's actually a feature that's a positive indicator that it's a person. And now you can imagine there are a lot of those features on the web. And so this learning algorithm and this learning algorithm have a grammar for features, and that grammar gets kind of grown. Well, all 3 of these have that property. It's not really a fixed feature vector. It's like everything that's on the web can become a feature, but it doesn't get considered explicitly as a feature by the learner until it sees it actually occur with some noun phrase. So in that way you can virtually have a virtually infinite set of features, but then the ones that are actually being considered by the program are just the ones that it sees instantiated on the web. Okay, but the point is here, somebody asked, well, do you have to just use 2 functions? No, 3 is better. So Nell does that. Yes?
Slightly off topic, but for this, do you trust certain websites more than others? You wait? Like,
No, we don't. So Nell just trusts all websites
all
equally.
information is equal.
Probably a really big mistake, but that's what it does at the moment. And as long as the majority is truthful, it will be okay. But it will be even smarter if somebody said, well, I'm going to fix it so that it could estimate which web pages are trustable. It doesn't do that, though. Yep?
Can Nell learn two contradictory things as true?
Yes, Nell often learns 2 contradictory things as true. So, for example, it believes right now that Bush is president, and it believes that Obama is president. And it has been told that president is one of those things that can only have one of. So there's some inconsistency in there. And it doesn't yet take advantage of, it doesn't yet even notice that inconsistency, but that's another kind of constraint for coupling that would be useful in principle. We just haven't done it. So let me finish the story about coupled functions. So here you get the idea. This is exactly what we're talking about in co-training. But once you have this idea that, oh, well, this kind of coupling functions really helps make unlabeled data valuable, right? And just to emphasize that. In this case, what this means is for every single unlabeled noun phrase that Nell can find, and that's a lot, like 50 million of them that it finds that occur at least 40 times. So it's 50 million unlabeled noun phrases. For each one of those, it may not know whether that noun phrase refers to a person, but it knows that this function, the blue function, and the green function must all agree. That either they should say yes or they should say no, but if there's disagreement, something's wrong and something's got to change. And if you had 10 unlabeled examples, that would be pretty valuable. If you had 10,000, it'd be really valuable. If you have 50 million, it's really, really valuable. So the more we can couple, given the volume of unlabeled data that we have, the more value we get out of it. Okay, but now you don't actually have to stop there. We also, Nell has also got about 500 categories and relations in its ontology that it's trying to predict. So it's trying to predict not only whether a noun phrase refers to a person, but also whether it refers to an athlete, to a sport, to a team, to a coach, to an emotion, to a beverage, to a lot of stuff. And we can couple the training of functions not just this way, but we can also couple it this way. Right? So for the same noun phrase, Nell is going to be training independent functions represented by those different black arrows. And we tell Nell at the beginning, when we define the ontology, we say athletes are a subset of people. Therefore, it knows that there's some coupling constraint between the function it's trying to learn for athlete and for person. Namely, that given an unlabeled noun phrase, there are certain joint assignments of athlete and person labels that are okay and others that are not. You can say not an athlete, not a person, that's okay. You cannot say not a person, yes, an athlete. That would be bad. Okay, that's an indicator that one of those two functions is wrong, in the same sense that this kind of co-training view would tell us one is wrong. Okay, so Nell actually uses constraints on different output labels that it's trying to learn. And it learns each of those black arrows is basically a Boolean classifier that Nell is learning. So if you put those two ideas together, you get this nest of coupled functions trying to learn a whole bunch of different labels that have some constraints about what are legal joint labels and different views for each of those. When you multiply all that out, well, let me just say there's one more part of it, and then I'll get to this question. The final part is it's not just learning to categorize noun phrases, it's also learning to extract relations. And those relations are extracted by training classifiers of noun phrase pairs, like Bill Gates and Microsoft. Is that an instance of the athlete plays sport relation? No. But it's some other relation, yes. So it has a bunch of classifiers for different relations. These are classifiers of noun phrase pairs. When we define a relation like athlete plays on team, we also tell Nell what's the domain and the range. What are the argument types? That relation requires an athlete and a team. And separately, it's learning these things to classify things as athletes or teams. So that gives it the final kind of coupling constraint, which is that all of those functions that are trying to classify the individual noun phrases into categories like athlete, they've got to be consistent with the pair of noun phrase classifiers that are trying to extract the relations. You can't say athlete plays on team if you're talking about something that's not a team and not a person. So that gets us another set of coupling constraints. So I guess this number is a little bit out of date, but when you multiply it all out, there are close to 2,000 now of these black arrow functions that it's learning. And it's just this simple idea of multi-view learning or coupling the training of multiple functions with some kind of consistency constraint on how they must agree, what's a legal set of assignments they can give over unlabeled data. It started with a simple idea in co-training that two functions are trying to predict exactly the same thing. They have to agree. That's the constraint. But if it's a function like, is it an athlete and is it a beverage, then they have to agree in the sense that they have to be mutually exclusive. And so we can impose a variety of different types of constraints we have. And then the final, well, let me stop there because I saw a few hands up that I was ignoring along the way. I wanted to just get through the core part of the story, and that's it. So were there questions? Yeah.
So about these constraints that an athlete is a person but not a sport, did you say that they were, that Nell learns those, or are they input?
Good. So the question is, how does Nell get these constraints? Are they given or are they learned? For the most part, they're given. So when we define the ontology at the beginning, we said athlete is a subset of person. But remember that rule that we saw that said if a person plays in the MLB, then they play baseball, or it said something like that. That's actually an additional constraint between these two relations. Person plays sport, baseball, and person plays in league. And that constraint was learned by Nell. So we started it out with a whole bunch of these. But one way you can think of that rule learning that it's doing is that rule learning gives us additional coupling constraints among. So, for example, why can I not do that? For example, there's a rule that says if an athlete plays on a team and the team plays sport S, then the athlete plays sport S. That's one of the rules Nell has also learned. And you can think of that as an additional constraint between these three relations, right? That we didn't put in by hand, but that it discovered as a probabilistic constraint in this case. From just the empirical regularities among the stuff that it has read. So this comes back to the idea of I want to build systems that are learn in a more cumulative way and that have the characteristic that once they've learned X, then they're in a better position to start to learn Y. And that we get some synergy. So this rule learning, that we saw that one rule in the knowledge base, there are somewhere between 600 and 1,000 rules in there at the moment that Nell has learned on its own. That's a perfect example of a kind of property we'd like to see more of in Nell, right? Because when it started off in January of last year, the knowledge base was empty except for the handful of labeled examples we gave. There was no way it could have learned that rule. Didn't know enough. But after it had read for months and populated, it now has, I don't know, probably thousands of athletes and 100 or so sports and lots of teams and lots of relations. Now it's got a big enough knowledge base that it can actually learn these empirical regularities about the world that it's reading about. That allows it, those empirical regularities, to become additional coupling constraints that give it even more leverage out of the unlabeled data to go back and retrain these black arrow functions that it currently has an approximation to. So this kind of nice virtuous feedback loop is kind of hard to characterize. So when I said that there were actually three, I think, good ideas in Nell, the first one is if you're going to do semi-supervised learning on a large scale, the best thing you can possibly do is not demand that your system learn one function or two, but demand that it learn thousands that are all coupled, because that will give you the most, allow you to squeeze the most information out of the unlabeled data. So that's idea one. Idea number two is, well, if getting this kind of coupled training is a good idea, how can we get more constraints, more coupling? And so good idea two is have the system learn some of these empirical regularities so that it can add new coupling constraints to squeeze even more leverage out of the unlabeled data. And good idea three is give the system a staged curriculum, so to speak, of things to learn, where you started out with learning easier things, and then as it gets more competent, it doesn't stop learning those things. Nell every day is still trying to improve every one of those noun phrase classifiers. But now it's also learning these rules and a bunch of other things as it goes. So, in fact, maybe I can just, no. I have to, 5 minutes. Let me tell you one more thing that links into our class. So the question is, how would you train this thing, really? What's the algorithm? And probably if I asked you that and you thought it over, you'd say EM would be nice, right? So you think about it this way. It's basically a very large
semi-supervised learning problem. If we wanted to apply EM to it, and we had infinitely big, fast computers, then here's what we would do. We'd say, okay, we're trying to learn these different functions that classify noun phrases into these different categories and classify noun phrase pairs into these different categories. We have a large collection of text. And so let's use EM. We'll start with the labeled data. We have a lot of unlabeled data, too. On every E step, we will re-estimate the labels for every one of those unlabeled examples. What are the unlabeled examples? Every noun phrase on the web. And every noun phrase pair on the web. Okay, but let's not worry about tractability. In principle, this is what we'd like to do. We'd like to run EM. So we could have an EM process where on the E step, we re-estimate the labels of every noun phrase and every noun phrase pair for every one of these functions Nell is learning. And then on the M step, what do? We just take those expectations and we use them to retrain all the classifiers and for all the noun phrases and noun phrase pairs. And we iterate. That's EM. Okay, now, it's a good idea in principle. In practice, we got a problem. We've got too much data. And so we can't exactly do EM because Nell routinely works with 20 million noun phrases, and that number squared if noun phrase pairs. It just takes too long to do the E step if you've got 10 to the 14th labels you've got to fill in. Also on the M step, remember those features that we looked at? Like every URL with every HTML token string is a potential feature. There are a lot of those, too many of those features too. So what Nell does is what I think of as E prime M prime. It's like EM, except it cuts corners. It's an approximation. On the E step, instead of labeling all of the 10 to the 14th noun phrase pairs, it just labels the ones in which it's most confident, given what it currently knows. And it's allowed to add 250 new labels, 250 new noun phrases that it labels for each function on each iteration. So you think of the E step we'd like to perform has 10 to the 14th labels. And what it's really doing is, that's a virtual set of labels. It's not really doing them all. It's just doing a growing subset of those, a subset in which it's most confident. So that makes it somewhat tractable. And what that means is the knowledge base itself is the result of the E step. The knowledge base we were browsing, that is the set of labels, along with confidences, probabilities, for every function in every noun phrase. So when we looked at Pool Joe as an athlete, that was part that we were examining the labels assigned during the most recent E step. It is the knowledge base. That is the set of latent variable labels. And then the M step, well, it's like the M step. We use that knowledge base to retrain all these classifiers, except again, not using every conceivable feature in the grammar, but just using the ones that actually show up and have high mutual information to the thing we're trying to predict. So just like in the E step where there's a virtual, very large set of things we could label and we just do a growing subset, similarly for the features, x1, x2, xn, it's just looking at a growing subset of that very, very large set of features too. But other than that, it's pretty much like EM. And there are some other approximations in there too, but this is the basic idea. So, so let me end there. And I just end by saying two things. One about the idea here. So I do think this is, even though this is a course that's supposed to be an introduction in machine learning, you're really now already in the position where you can pick up research papers and read them and make sense of a lot of them.
And I thought it would be fun to talk about this one example of an ongoing research project, because you can see how it really does use very much the ideas we've been talking about in class. Second quick comment, one of the data sets that we're making available for the projects is a data set collected by Nell. It's an array of, well, we have different versions of it, but it's an array of the n most frequent noun phrases found on the web and the nk most frequent language contexts found on the web. Language context would be like mayor of X, or I like X, or home run hit by X. So we have the n most frequent noun phrases and the m most frequent contexts, and the ijth entry is just how often those co-occur. This is a pretty interesting data set, and we have different versions of it. I think the one that we point to currently on there has maybe 100,000 or something like that, 100,000 by 100,000. We have a version that's 20 million by 50 million if you prefer, but you probably don't want to start there. But it's an interesting data set to think about, and there are a lot of different tasks one can do with that. So just wanted you to be aware of that. All right, thanks. See you next time.